And what up, ladies and gentlemen of AP Physics? It's Mr. Simkins back with you in the Simkins Physics Corner. Tonight, we are kicking in our Kinematics Week 3 launch, so let's get right to it. First, as I said at the beginning of the course, every Monday you get your homework assignment. Boom, there it is. It's 27 questions, I believe. This is just talking about how many students have done it. So do not do them all on Friday. That would be a terrible idea. So every Monday the homework drops, every Friday the homework's due. Check out Albert, and your homework assignment is up there for you. Let's introduce kinematics. All right, so do you guys know the tale of the German kids, Hansel and Gretel? Yes, they went on a trip through the woods, and they had this brilliant idea to track where they had gone by breaking off some pieces of breadcrumbs. So they're like, when I turn around, if we get lost in the woods, I can just go back and follow the breadcrumb trail home. Well, here's the thing about breadcrumbs. Woodland creatures find them absolutely appetizing. And so what happened is Hansel and Gretel, they dropped all these breadcrumbs. They had a great time. The sun starts going down. They say, let's head on home. They turn around, and all the little woodland creatures had eaten up their breadcrumbs. Without GPS cell phone service, now they were lost in the woods. And the tale continues. I'll let you look it up. But let's talk about what this might look like if these kids are walking through the woods. Now, I don't know if you know anything about Germans. They are known for their precision, German engineering, right? And so the precision of these children is just ingrained from the very start. And this little German child here, I believe that would be Gretel, I believe, she knows exactly every 5 seconds to drop a breadcrumb, just with that classic German precision. So boom, 5 seconds, boom, 5 seconds, boom, 5 seconds. And if we can count on the precision of these German children, it's ingrained in them. If we know they are precise, we know that she dropped these breadcrumbs exactly every 5 seconds, what could you infer about the motion of Hansel and Gretel if we found a breadcrumb trail that looked like this? Oh, they were moving at a constant speed. And how would I know that? Because if we can know that time is built into each breadcrumb drop, 5 seconds for every breadcrumb, and the distance between each breadcrumb successively stays the same, they're moving at a constant speed. All right, and then we can also look and say, okay, well, what if the breadcrumbs at some point then, she's still dropping them every 5 seconds, what if the breadcrumbs look like this? So they were spaced close together and then farther and farther and farther, but she's still dropping every 5 seconds. We would assume she is speeding up. All right, and then if we say, oh, maybe the breadcrumbs, I come upon the breadcrumb trail and it looks a little bit like this, what would you assume then? Of course, well, if this is 5 seconds and then we travel less distance in 5 seconds and less and less and less, we're slowing down, okay? So kinematics is the part of physics that talks about motion. And I don't know if you've seen some of these pictures right here where you take like a series of pictures and then you stitch them all together, all right? And so what you see here, we can infer how this person is moving based on the spacing between each successive picture. So today we're going to talk about distance and displacement, speed and velocity, and we're going to talk about acceleration, one of my favorites. So here's all the physics that's in this lesson. I'll move myself over here. We're going to talk about first scalars and vectors. All right, so this is just fancy terms for the types of quantities we're going to encounter. A scalar quantity has a magnitude only. What's magnitude, you ask? Well, it's just how large something is relative on our scale. So let me give you an example. If I step on a scale, I get a scalar quantity. Why is that, Mr. Simkins? Well, because if I step on a scale and it had a voice, it would say 156 pounds, right? Now, what it wouldn't say is 156 pounds northeast. That would be totally silly, right? A scalar quantity only has a number associated with it, not a direction. Well, what kinds of quantities do have direction, you ask? I'm glad you did. A vector quantity would have direction. It has a size and a direction. So a good example of this might be if you're playing Tiger Woods golf on your Xbox over the lockdown summer, right? And you look and it has a little windmill thing, or maybe you're playing the newest NFL game or whatever, and you're trying to make a kickoff. All right, that little wind speed vector might look a little something like this, 5 miles per hour, and in this case it would be northeast, right? So that would be an example of a vector quantity if it has magnitude, the number, and direction, the direction. All right. And so as we unpack some terminology today, we're going to start with distance and work our way down. You notice that everything in this side of the table is a scalar and everything on this side of the table is a vector, and we're going to return to this slide at the very end to recap everything. So without further ado, let's jump right into it. All right, displacement. Displacement is on our vector side, which means it has a direction, okay? And so displacement is defined as your change in position. And so if you guys have seen Despicable Me, I believe it was back in the day, this guy, his name is Vector. He's like, Vector, I'm committing crimes with both magnitude and direction. Oh, yeah. So if you've seen that clip, this term of vector is actually already burned into your brain whether unfortunately or not with that bodily motion there. But distance is going to be our scalar version of how far we went, and displacement is how far you went from where you started, or more specifically, your change in position. So if you see something that says delta x, we're talking about displacement. And let me give you, and both of these things though, both distance and displacement will be labeled in meters. So if you see meters, we're talking about some kind of distance. Let's look at a quick example of the difference between distance and displacement. Say that 3 times fast. If I start over here and I end over here, okay, how far did I go? I need more specific than that. See, we're very precise as scientists. Distance, are you asking me about distance, Mr. Simkins, or displacement? Because if you ask me about distance, I would say, well, I walked 10 meters, then 4, then 8, then 6, then 3, then 2, and if I add them all up, I would get 33 meters. But if I ask you, how far were you displaced from point A to point B? Well, you would say, how far did I go from displace to that place? No, seriously. All right. Displacement is how far you went from this place to that place. It's the change in position. It's where did you start and where did you finish? And delta x, or displacement, would be the difference between those two. It would be x minus x initial. So if you do the math there, it would be 21 meters. How did I know that? Well, I just looked at the numbers that would tell me about the length of this red line down the middle. 10 plus 8 plus 3 would get me 21 meters. So distance is everything counts. Everything that you walk. If I go back to this slide before here, everything counts. That's what I mean when I say everything counts. I mean every step that you take adds to your distance. But displacement is only concerned with the difference between where you started and where you finished, or how far you went from this place to that place. Oh, it never gets old. It never gets old. Maybe it does for you. Let's talk about velocity and speed, all right? Let's go back to our scalars and vectors. So a scalar is something with only magnitude. So if I say I'm going 5 miles per hour, I'm telling you my speed. If I tell you that I am going 10 miles per hour south, that would be a vector because it has a direction. So speed is distance over time. Velocity is defined as displacement over time. So you see already we need to know about distance and displacement because now they're going to trickle down and affect our definitions for speed and vector. All right. Now let's take a quick look at velocity. This little bar here means average. That's what that symbol means. And so this equation actually says average velocity is displacement over time. And there's a reason behind that. Let me give you a quick little pro tip for how to live safely and not get a ticket. So my official advice is to always drive the speed limit, of course. But in some cases, you may find yourself in a little bit of a hurry, but fortunately, your friendly neighborhood police officer has painted these white lines on the road to remind you to obey the speed limit. What do you mean, Mr. Simkins? Well, next time you drive around, look for these things. They're all over the place, especially in small towns. They're white, bold lines painted perpendicular to the road. And maybe you didn't know what they were there for. Maybe they didn't go over that with you in driver's ed class. Well, let me give you a tip for how this works. Let's say the speed limit here is 35 miles per hour. You should drive 35 miles per hour. If you happen to have a lead foot here and you're driving maybe, I don't know, 40 miles an hour, a little too fast, right? If you're driving 40 miles an hour and you come in here, well, by the time you get from point A to point B, what happens is the police officer will be timing you, and they have a little table of the distance between these two white lines. Whoever they say, go paint these white lines, please. The people paint the white lines and say, here you go, Mr. Police Officer, this is how far apart the white lines are. They know your distance, and they will time you. So they have distance over time. They will calculate your average speed. But the key here is they calculate your average speed. So let's say you're coming in here. When you hit this first point, if you're going 40, are you over the speed limit? Yes. Could they give you a ticket? Yeah, it might be annoying, but they could, right? Okay, but technically you are going over the speed limit. However, if you realize the error of your ways and you see these white lines as a helpful reminder, and you happen to hit the brakes, and by the time you arrive at this point, you are now have reduced your speed to 30 miles an hour, what would your average speed be? Oh, gee, the average of 30 and 40 is 35. And so that police officer, if they were timing you and did distance over time, they would say, congratulations, you are following the speed limit. Your average speed was 35 meters per second. So that's when we talk about average speed, okay, or average velocity. Now, when we talk about instantaneous speed, that would be your speed at a particular instant, a snapshot. And so if they had one of these puppies right here, a radar gun, as soon as you come around the turn, if you're going 40, whoop, whoop, they're going to get you, all right, because that is your instantaneous speed. Let me show you what this might look like on a graph. As we unpack this week, we're going to look at more graphs, but let's say we graphed your position versus time for this story I just told you, all right? In the beginning part of this, you're going a little fast. See, you're covering a lot of distance in a small amount of time. That's why it has a steep increase in slope on your position time graph. Again, we're going to unpack this all as the week goes on. Now, you say you slow down at this point, right? You notice that the steeper the graph is, that would indicate we're moving faster. Just like with Hansel and Gretel, the further apart the dots were spaced, the faster we can imply that they're going. The same holds for a graph of position versus time. The steeper it is, the faster you go. The slope is associated with the speed. So your speed at the beginning was too fast, you slowed down, and guess what? If you take the average, it's somewhere in between. So you might have to come back to this slide later in the week when we talk about graphs, but there's just a little helpful little hint as to what is coming later this week. Finally, the last term for the day is acceleration. Oh, that guy. If you can find that video, it's amazing. Acceleration. Justin Higgins, my man. It is the rate of change of velocity over time. So if you drop a ball off of a cliff, it will speed up, and it will speed up, and it will speed up because it is accelerating due to the unbalanced force of gravity on it. Let's talk about acceleration for a little bit. See, the biggest thing that people get mixed up when they talk about acceleration, you got to go back to the definition. Acceleration is when velocity changes. If velocity changes, that means it's your speed in a direction changing. Oh, there's two pieces, aren't there? You see, if velocity is a vector quantity, which means it has both, I'm going to abbreviate here because physicists are lazy, magnitude and direction, what does that mean? Well, a lot of people would say, oh, you accelerate when you speed up, which is not an incorrect statement, but there's more. Because if you are speeding up, your velocity is increasing. Is your velocity changing? It sure is. But remember, acceleration is when velocity changes. What if I'm going fast and I slow down? Is that accelerating? It is. So the three ways to accelerate are to speed up. Sorry about my terrible handwriting. We're going fast. I'm trying to keep it under 15 minutes. To slow down. And the third one is very elusive. If I'm going at a constant speed and I come into a turn and all of a sudden I go around this turn keeping the same speed, you may be tempted to say, well, your speed's not changing, Mr. Simkins, but your direction is. Oh, and velocity has direction. If velocity has direction and I change my direction and acceleration is a change in velocity, then that's the third way to accelerate, is to change direction. So yes, even if you go around the turn at a constant speed, you are changing your velocity because you're changing your direction. You might need to stop the video and go back and rewatch that because that's important. All right. So what that means is, if you have ever heard someone say the word deceleration, you should put on your Thanos fist of power and snap that word out of existence, because deceleration is not a sufficiently descriptive term for our physics. Why, Mr. Simkins, do you hate the word acceleration so much that you want to annihilate from the universe? Well, it's because we need to know more about when we talk about acceleration, all right? Because deceleration, that confuses people. Here's what I mean. Positive acceleration is always a change in velocity to the right, and negative acceleration is always a change in velocity to the left. Well, what if I'm moving to the left? If I'm moving to the left, velocity is to the left, and I'm accelerating to the left, am I decelerating? No, I'm actually increasing my speed in the negative direction. Look at this picture for a second. It'll make sense to you. If the acceleration is the change in velocity, sorry, the picture is actually up here. If my velocity is small and then it gets bigger in the negative direction, and then my velocity gets bigger in the negative direction, I have negative acceleration and negative velocity, and I speed up. So that's why I don't like the term deceleration, because it gets people confused. I'd rather you use positive acceleration, indicating it's to the right, and negative acceleration, indicating it's moving to the left. Because again, acceleration is a vector quantity. It has direction. So the quick recap, you can take a pause of the video and just digest this. Here's your AP Physics equation sheet. There's what all the variables mean, and you can come back to this slide and write it in your notes to help you out. Let's look at a quick story to wrap up for today. If I have a thing and it rolls down a ramp, I want to draw the position, velocity, and acceleration pictures for this. Well, when you roll down the ramp, what are you going to do? Aren't you going to speed up? And if I speed up, oh man, we're going to get into this week, my position time graph will look like a curve. Why? Because the slope is the speed, and if I'm speeding up, my slope should be getting bigger and bigger. The velocity, it says we started from rest, so our velocity is 0, and our velocity will steadily increase. That should be a straight line. If it doesn't look like one, it is. We're going to unpack this all week. And if I have a positive velocity, brain teaser of the day here, the slope of the velocity graph would be rise over run. What's that? That's acceleration. So if I have a positive constant velocity, I would have a positive constant acceleration. All right, to dive across the finish line for this one to make 15 minutes, we have less than 30 seconds left. Here's all the physics that I want you to know from this lesson. Be sure to go ahead and check out this to put it in your notes. We have scalars and vectors, distance and displacement, speed and velocity, and acceleration. Boy, did I just make it. Make sure you check out the homework and stay tuned this week for more details on that graphing stuff. I'm Mr. Simkins in the Simkins Physics Corner.